In this video, we're going to concentrate on Le Chatelier's principle. So before watching this, you should have watched the introduction to chemical equilibrium video, going through what it means for a system to be in equilibrium, the meaning of static equilibrium, dynamic equilibrium, and a dynamic state, and also how to find an expression for the equilibrium constant Kc. So if we talk about Le Chatelier's principle, okay, when a system in equilibrium is subjected to a stress, the system readjusts to relieve the effect of that stress. Okay, so some of the stresses that can include are pressure, temperature, and concentration of one or more of the reactants. Okay, so we'll come across all of these in this video. Okay, so changing the position of equilibrium, we will come on to what that means in a little bit more detail when we look at some examples a little later on. It's a little easier to see when we're talking about color changes of solutions. So we will come on to that later. If a system is in dynamic equilibrium and the conditions are changed, the position of the equilibrium moves to counteract that change. Okay, so that's just a different way of wording what we had as our definition of Le Chatelier's principle in the previous slide. Okay, one of the things we can change then is changing temperature. Okay, so whenever we're thinking about chemical reactions and we mention temperature, one of the first things that should pop into your head would be whether we have an exothermic or an endothermic reaction. So exothermic ones which give out heat into the environment, okay, so they lose energy, and endothermic then is that they gain energy. Okay, so the energy of your products is greater energy than what you had at the beginning with your reactants. Okay, so reactions that are endothermic, if you increase their temperature, it increases the yield. Okay, so that basically means is that we say endothermic reactions, they take in energy. So if you increase the heat, okay, amount of heat energy in that area, in that system, that's more heat energy for the reaction to take in. Okay, so that increases the yield. If you decrease that temperature, it doesn't have as much energy around it, or energy in that system to take in, so your yield is also going to decrease. Okay, so for endothermic reactions, if you increase temperature, you increase the yield, decrease the temperature, decrease the yield. For exothermic then, you're giving out heat. Okay, you're releasing energy, releasing heat energy. Okay, so if you increase the temperature, that actually decreases the yield. If you decrease the temperature, you increase the yield. Okay, so looking at an example, alright, this is the production of ammonia through the Haber process. Okay, something which we will be looking at in greater detail. For this, we're going to look specifically at the effective temperature for the moment. Your delta H figure for this reaction is minus 92 kilojoules per mole. Okay, this minus here means, oops, okay, right, the minus before that 92 means that the reaction is losing energy, it's giving out heat. Okay, it's losing 92 kilojoules per mole. Okay, so that means it's an exothermic reaction. That means if you increase the temperature for this, the forward reaction, the yield is going to decrease, while your reverse reaction, that is actually going to increase. Okay, so your forward reaction is exothermic, your backward reaction here is endothermic, because that would be plus 92 kilojoules per mole. Okay, so forward reaction, as I say, was promoted by a low temperature, while your backward reaction is promoted by a higher temperature because it is endothermic. The second stress we look at, okay, is pressure. If you increase the pressure of a gaseous reaction, it will favour the reaction that produces the least number of molecules, while if you decrease the pressure, it favours the reaction that produces the most number of molecules. Okay, so if we take the same example of our Haber process where we just have nitrogen and hydrogen, right, we're not concerned about N2 or H2 or H3 over here. What we're looking at here are just the figures that come before them. Okay, so this N2 here, there's 1 molecule, 3 molecules, 3 hydrogen molecules or 3 H2s, and here then we have 2 molecules of ammonia. Okay, so overall this side we have 4 molecules, and on this side then we have 2 molecules. Okay, so if we increase the pressure, that's going to favor our forward reaction because we're producing less molecules. We're going from 4 molecules to 2 molecules. If we decrease the pressure, it favors the backwards reaction, where we're going from 2 molecules to 4 molecules. Okay, when we talk about changing the point of equilibrium or shifting equilibrium left or right, that's what we're talking about. Okay, so which way is the reaction being favored towards? Okay, so the Chatalier's principle predicts that in all gaseous reactions, an increase in pressure will favor the reaction that brings about a reduction in volume. Okay, that's just a reduction in the number of molecules. Okay, it will shift towards the side with the smaller number of molecules. Okay, this is a picture that is in Chemistry Live, the Leaving Cert textbook. Okay, it's just a bit of a visualization for you. Okay, so here, like we had before, you have 4 molecules. You have 1, 2, 3, 4. Over here, you just have 2. Okay, so here you have less pressure, or you can also say you have a greater volume there as well. Okay, so that's what they were talking about here at the bottom of this slide here. Okay, so you have a greater volume here, you have a less of a volume, or you have an increased pressure. Okay, so that is just a small visualization for you. Now, okay, so there are 3 experiments we have to look at to investigate Le Chatelier's principle. Okay, the first one is using cobalt chloride. Okay, and the addition of hydrochloric acid to it. Okay, so this side of your reaction where your, I suppose, reactants are is blue. Okay, and your right hand side of the reaction then, the colour that's associated with that is red. Okay, if we add hydrochloric acid, okay, your equilibrium is going to be shifted from the right to the left. Okay, so you're going to shift from red to blue. Okay, you're increasing the concentration of hydrochloric acid on this side. Okay, so if you increase the concentration on this side, you're going to shift equilibrium to the opposite side. Okay, so you're always going from a region of high concentration to low concentration. So if you increase the concentration of hydrochloric acid on this side, well then you're going to shift equilibrium in the opposite direction. So it's going to go from red to blue. Similarly, if you add water, okay, you're going to increase the concentration of water on this side, and I suppose specifically you're really looking at H+. Okay, so that's going to shift it to the right, so you're going to go from blue to red. Now, okay, so if we look at the addition of heat then in this, alright, we are looking to see what effect increasing the temperature would have. Okay, so if you were told in a question that the increase in temperature results in this system going from red to blue, then you could say that your forward reaction is exothermic. Okay, that is because this increase in temperature goes from red to blue. Alright, that is shifting it from your right hand side to your left hand side. Okay, if you increase the temperature and your yield increases, okay, or it goes from red to blue, so you're increasing your yield of this side of your equation, you're producing more of it, so your yield is increasing. Okay, that means it's an endothermic reaction. Your yield increases when you increase the temperature in an endothermic reaction. When you increase the temperature for an exothermic reaction, your yield decreases. Okay, so your forward reaction here is exothermic, your backwards reaction is endothermic. Your second example then, sodium dichromate. Okay, the addition of an alkali, NaOH, here will result in a shift from orange to yellow. Okay, an addition of hydrochloric acid then will shift it from yellow to orange. Now, your third example then, iron chloride potassium thiocyanate. Okay, so here this is the same reaction. Okay, so both sides of this slash, it's the same reaction that's taking place, just this one is a little bit more detailed. Okay, so if you add hydrochloric acid, it changes from red. Okay, so this side is red, this side is yellow. Okay, so exact same as what's over here. Okay, so if you add hydrochloric acid, it changes from red to yellow. Okay, so again, increasing your concentration of hydrochloric acid, increasing your concentration of Cl- will shift equilibrium back over to this side, so it will go yellow. Add some thiocyanate. Okay, so that's your thiocyanate. If you increase the concentration of that, you have more of it there to participate in this reaction. Alright, so that will shift your equilibrium to the right. So you will end up with a solution that is red. Okay, like what is present in the diagram there at the bottom of that slide. Okay, and that is also present in your textbook. Okay, so to accompany this video, I would suggest that you read the pages in Chemistry Live associated with these examples for maybe a more detailed explanation if you didn't understand anything in this video. If you know everything I said in this video to that detail, you are good to go for your leaving cert for equilibrium.